Hello again and welcome. Today we're going to be looking at some of the leads that were supplied with these Kasuntest meters. I've run benchmarks before using test leads that were supplied with some of the meters that I purchased, and I thought what we could do today is maybe take a look at how robust these leads are compared to some of the other ones I've tested. So if you haven't seen the video that I made previously where I've tested some of these leads, have a look at it. I'll share the link in the description. Again, this Kasuntest is highly modified. It survived a 14,000 volt plus hit. One of the things I'd done with the meter is I changed the fuse size out. Actually, this is the fuse that belongs in the meter, but this is what it originally came with. So another thing I thought I would do in this video is compare the current input of this meter compared with the standard one. So this is looking at the IEC standard 61010-2-033, and this is section 101.3.2, protection by a certified overcurrent protection device. In the very last paragraph of this, it says if the protection device is a fuse, it's replaced with an open circuited fuse. If the protection device is a circuit breaker, it's set to an open position. A voltage of 2 times the highest rated voltage for any terminal is applied to the terminals of the overcurrent protected measuring circuit for 1 minute. The source of the test voltage shall be capable of delivering 500 VA. During and after the test, no damage to the equipment shall occur. So what I've done is I've removed the fuse from this particular meter. I do not have a 500 volt VA power supply, but I do have a high voltage power supply. Now again, this meter, because it's modified, the input voltage will get clamped at about 800 volts. These are normally rated to 1000 volts. So I think it's only fair that we test this one at 2000 volts. And then what we're going to do is the same test for this ANIG 8008 and this unmodified Kasuntest ZT102. Now these two meters, I've never tested this current input, so this should still be fine on both of these. So again, this is my ESD gun, and this is capable of outputting a DC supply. Again, it's pretty limited as far as the current. It's certainly not 500 VA. What we're going to do is turn this up to 2000 volts. And again, this meter is accurate enough for this, and you can see this is live. And what we're going to do again is just plug this right into our current input. And now we're going to let this sit for 1 minute. Okay, we're past 1 minute. It's easily survived 2000 volts. Let's try taking this up a little higher. And again, the standard's only calling for 2 times the maximum input voltage. There you go. So even at 3000 volts, this modified input doesn't have any trouble with it. Alright, we're going to do the same test with the unmodified Kasuntest ZT102. Again, we'll just take this up to 2 kV. And there's 1 minute at 2000 volts. Let's try taking it up to 3. You can see no problems at all. Kind of curious where it breaks down at. There's 4 kV. Right there. So about 4,750 volts. Again, let's just try that with our modified meter. And we'll go ahead and turn up the input voltage. Oops. Go to the right set of leads. Alright, there we go. Alright, so there's 4.6. There's 5.5. That's the maximum we can put out, so just shy of 6,000 volts. Let's just let it sit there. See if it'll hold this at a minute. There you go, 1 minute at 6,000 volts. Alright, so this is our ANIG AN8008. Again, we'll just take the fuse out of it. And let's just try it at 2000 volts. Again, both of these meters have been damaged. So there's 1 minute at 2000 volts. Let's go ahead and increase this to 3000. It seems fine. Let's go ahead and take this one up and see where it breaks down. Oh, So right around 4,000 volts. So this 8008 is a little worse than the ZT102. But again, the very first sentence of the IEC standard, you're supposed to replace it with a fuse that's open circuited. So here I have one of the fuses that came from one of these ZT102s that had opened up. And we can see with a fluke here, it's basically an open circuit. So let's go ahead and we'll change out the fuse in the AN8008. And of course the reason that they want you to run this with an open fuse is the end caps extend beyond the clips in this case. So you can see that could actually affect the voltage that it breaks down at. Let's just go ahead and we'll reconnect the meter. So it was breaking down at 4100. We can see it's going right across the fuse cap. This is looking at table AA.1 out of the IEC standard, and you can see for our measurement category 2 we're less than 10 kiloamps of current, and for category 3 we're less than 50 kiloamps, and for category 4 we can be much greater than 50 kiloamps. See, the short circuit current is calculated for 1000 volt line to neutral voltage and a minimum loop impedance. The values of the loop impedance, insulation impedance do not take into account the resistance of the probe assemblies and the impedances internal to the measuring equipment. These short circuit currents vary depending on the characteristics of the installation. So of course we don't have a way to generate a whole lot of current. So I think what we're going to do is use these transient generators to attempt to blow the fuses in these 3 meters. So I'm going to try to capture this with a high-speed camera. Again, this is the ASTM fuses that were supplied by Dave. I don't expect these are going to be any problem because these are sand filled. The ones that come with these meters, on the other hand, are not sand filled. They're just a ceramic body type fuse. And what I'm worried about is once that gas inside ionizes, you know, is it possible that we could actually split the ceramic there? I have no idea. When we had damaged the fuse holder on the 1 meter, when I hit it with this transient, what actually happened is this piece down here opened up, and of course we vaporized the traces, so the fuse never saw the full energy of that transient generator. Alright, so the way I have this thing set up is the high voltage transient generator is going to put out about 1000 volt hit, and then that's going to hopefully trigger up the secondary transient generator, which is going to supply us a fair amount of current, not a whole lot, but should do something maybe to the fuse. It should at least open it up. So we are set to go, and we'll see how this works out. Well, I think that was it. Well, I gotta say that was pretty uneventful. It looks like we popped the fuse. Let me just apply the shorting bar. Alright, let's just go ahead and have a look at the fuse. So indeed it did open up. You know, to be honest, I would be more concerned about our little TVS down here. So let's just have a look at that. Again, this is a bi-directional part. Doesn't look like we shorted it. And it seems to read the same both directions. I'll tell you what, let's just put a new fuse inside of this thing and we'll see if it still works. This is just another one of the fuses that David sent. Same type. We'll just go ahead and plop that in. This will be putting out roughly 100 microamps. And you can see no trouble at all. So no damage to the meter. It actually survived that pulse. I was kind of a little concerned because, you know, I've never really tested that input before. So it looks like the fuse blows fast enough, even with a fairly substantial transient, to save the electronics. So not too bad. So let's just try that with our other meters. I don't know if this will show up in the camera or not, but these fuses are only rated for 10 amps at 250 volts. You know, and the meter is rated for 1000 volts. So technically when they run these, they're supposed to run them with 1000 volts across these fuses. So that's basically what I'm going to do with this. And again, if you remember, I snipped a couple of these fuses apart, and these are not sand filled. These are not a safety fuse. So there's just literally a fuse wire running between these two end caps, and it just gets sandwiched around the edges of this. So my concern with this, again being rated for only 250 volts, it doesn't have much in here for clearance. Once we ionize that gas and this thing breaks down, it's going to conduct a fair amount of current, and that second transient generator can put out a fair amount of energy. So I don't know what that's going to do to this area, but I'm ready to find out. So let's go ahead and set this test up and let's just see what happens. Alright, I think we are ready to go. So this will be the Kasuntest ZT102, and we have a 10 amp fuse installed, and here we go. Alright, so let's install the shorting bar and we'll have a look. Let's see what damage we've done. Down here, this is what's left of the fuse. Doesn't look like we cracked the ceramic, but the end cap is crushed. So I don't know what's happened there. But just look at the damage that's been done to the fuse holder. See how twisted those are? It almost looks like it's actually arced between the two of them, which again wouldn't surprise me. It doesn't look like it's damaged the trace between them. It's going from the ground up to our shunt, and we can see that's still intact. And let's go to the one side of the fuse holder. So that looks fine. So it doesn't look like it's opened up the traces at all. It literally just caused that fuse to rupture. Let's just have a look with this meter and we'll see if it behaves any differently. Alright, we have our safety stick removed. This will be the ANEG 8008. And again, this will be the same transient we just applied to the two Kasuntest meters. Looks a little different this time. Again, it looks like the fuse came out of it. You can see how much the two fuse holders have bent. You can notice all the copper plating down in here as well. Wow, it's actually broken the ceramic. This piece here is a small piece of ceramic that broke off of the body. You can see how sharp that is on the end now. So we actually ruptured the ceramic. There's the second end cap. Again, these are not a sand-filled safety fuse, so I'm not too surprised, I guess, that the ceramic ruptured. Alright, you can see I have our transient generator out. So this thing has been programmed to 15,000 volts peak. That's the same voltage that I ran all the test leads at the last time. Alright, so all I've done here is I've bundled up the leads. I'm just going to attach the transient generator right across the two inputs. And we'll be applying 5 transients and we'll see if the leads will break down. So that's 5 transients in case you're wondering if this is really live. So these seem to be fine. These are the leads that came from the Gardner bender. Again, we'll just repeat the same test. Make sure we get them all bundled up pretty close. So that's it, and it looks like the Gardner bender leads have no trouble with that. Again, these are our rebranded Vicor meter. Again, these are leads that would be supplied with typically the Harbor Free meters. And that's it. So no problems as far as insulation breakdown, even with the cheapest of the leads that I've checked. Alright, so you can see I have the laptop out and I've got some software. This is used to communicate with the power supply. That's sitting over here. And you may remember the last time I used this, I was testing the shunts out of the multimeters. Down here I have a couple of test blocks and I have some machined inserts. These are made to accept the probe inputs on the one side, so they plug in here. And then this side is made to attach to the banana connector. So we're going to be using this test rig to step the current through these different probe sets. I've done this before, and that can be seen in this software. This is all the data I collected previous, so these are some probes from Agilent, Amprobe. This was some Belden wire that I ran. Again, you can go back and look at those tests. The way we can run this, we go to post-process, add a waveform, and this, for example, is the Agilent test probes. So we could see these Agilent probes were dissipating about 19.7 watts. And this is looking at the resistance. Of course, as we continue to increase the current, the resistance goes up. So on the far left, this is the resistance of the probe. It's roughly 0.04 ohms. We currently have about 850 milliamps running through it, and it's dissipating about 30 milliwatts. What we're going to do is set this to closed loop. So we're going to increase this to 2 amps. Now as this probe begins to heat up, because this is running closed loop, this will just keep a constant current through the probe. So we're going to go ahead and run a sweep. We'll start it at 2 amps. We're going to increment 2 amps every 30 seconds until we hit a maximum of 20 amps. We'll just store this in a file called GBI for Gardner Bender Instruments. Alright, you can see we're at 20 amps right now, and our probe lead is dissipating roughly 13.5 watts. The resistance has been pretty constant. You can show that down here. So this is looking at the resistance. The top here is 0.0348. Alright, so next up I have the test leads out of the Vicor meter. What's interesting about these, look at the resistance on it. It's almost 0.6 ohms. The other one was 0.03 something. It's already dissipating 2.3 watts. Again, these meters are very cheap. Harbor Freight gives them away for free. Again, this will be the same profile as before. We're going to be incrementing 2 amps every 30 seconds up to a maximum of 20 amps. Look at this thing. We just now hit 4 amps. Software's already trying to get it up even higher. I think the lead's going to open up long before we ever hit the 20 amps. Alright, so I have some safeties built into the software where essentially if I'm trying to drive too much voltage across it, I'll cut it out. You can see the meter actually is marked 10 amps max. What I'm going to do is change our upper limit to double. And instead of the black lead, we're going to go ahead and install the red one. And you can see it's not much better. This bar graph down here gives you some indication of when I hit the safety limit. Once this hits 100%, this is where the software is going to kick the probe out. Again, you can see we're hardly getting started. We're already up to 25%. Leads are pretty much too hot to touch now. You can see they're dissipating roughly 55 watts. You can see they're actually starting to melt. The software just threw an error. They offer these basically for free from Harbor Freight. Not a real high quality lead, but you know, you wouldn't expect it to be. Alright, so what about the test leads that are supplied with this little Kasuntest? Again, we have quite a few of these. They're not very long. That's one of the things when you're running these tests. Obviously, as the leads get shorter, they actually could have a lower resistance than a long set of leads. Alright, so the probe's attached, and it's interesting because you can see the resistance is already about double what the ones were from Gardner-Bender. So not near as good as some of the other leads that I've ran. So let's just see how these do. Again, we'll run the same test, sweeping from 2 all the way up to 20 amp in 2 amp increments. And you can see we're dissipating roughly 34 watts right now. The resistance is really starting to go up. It's 0.08788. Leads are fairly hot to the touch. So this is looking at the power dissipation of the 3 leads. So the white is the Gardner-Bender, the blue is the one that came with the ZT102, and the red is from the Vicor. And you can see the Vicor is all the way up to 75 watts compared to about 35 watts on the ZT102. So this is all the leads that I've tested so far. This is looking at resistance. The very worst one is this Vicor. So let's just go ahead and deselect him. And the next one down the list is this one from Centec. We zoom into this a little bit further. This next one is from Klein Tools. You can see that's all the way up at 0.375 ohms. And now things start getting a little flatter. The interesting one is the bottom one down here. This is all the way down at 0.025 ohms. This was actually supplied with a Maztec meter. This one is a Maztec red and black. This next one is from the Vichy VC99. So this next lead is what was supplied with the ZT102. And you can see the resistance on this, again, about 0.07 ohms. The next one down is roughly 0.05, a little less than that. So it's not very good, and what's interesting again is the leads that come with that ZT102 are quite a bit shorter than the normal leads that you would get. So a lot of these are a longer lead and they still have a lower resistance. So the leads that I'm still showing, this is the Agilent. The red one here is from Amprobe. This is one of the leads that came with my Fluke 101. The blue trace is a lead from Unitrend. This next blue trace came off of my Hioki. This green trace is off of one of my ProbeMaster probes. This is an old style one. The next one is our Gardner-Bender. The next one on the list is the leads off of my good Bryman. This red one is my newer ProbeMaster probes. Again, this is a little different style. Again, these are gold plated compared to the old ProbeMasters that were actually a steel. So again, these are not plated. This is just stainless steel, where these are plated with some type of a gold. These both have a threaded end, so they both accept the screw-on accessories. And again, the ends on these are a little different. The newer style, again, has the sheathing, and the old style was a straight. So let's just have a look at the inside of these. It does appear to be double insulated. And this is what the wires look like. Not a whole lot of strands to them. This is the leads off of the Vicor. You can see it still has a double insulation. So what I did is I carefully cut out a section out of each test lead. This top one, this would be like your Harbor Freight meter. The second one down, this is out of the ZT102. And then this third one, this is what's used on the ProbeMasters. Again, this is a Belden wire. But you can see there's not very many strands in that Harbor Freight meter. There's definitely more in the ZT102, but neither one of these come even close to what that Belden wire looks like. So we're going to start with our piece of Belden wire. What I've done is I've stretched this between the two clamps. You can see this is 4 inches in length. And what we're going to do is we're going to start a sweep at 10 amps, and then we're going to increment by 10 amps every 30 seconds. And let's just see how this one little length of wire does. In the past I've done destructive tests on the test leads, and I've actually caused the insulation to catch fire. This will be a little bit cleaner. See, it's just starting to glow. This is all the way up at 80 amps right now. You just turn off the lights for a sec. Oh, it just burned open. Alright, again you can see we're at 4 inches, and this is going to be the wire out of our Harbor Freight type meter. And again, we'll sweep from 10 amps up to 100 amps or wherever it blows open, and we'll do that in increments of 10 amps. It's interesting, you can see it's already at 0.1 ohms, dissipating almost 10 watts. It's starting to turn black already. You can see it's starting to sag, and it's starting to glow red. And there, it just burned open. Nope. Burned a few strands open. There, it's opened up. And finally, this is the wire out of the ZT102 test lead. And again, this is 4 inches across. And we'll be sweeping from 10 amps up to 100 amps, again in 10 amp increments. And you can see it glowing red. I doubt it's going to hit the 40 amps. See, the resistance is just climbing. There, it just blew it open. Again, this is looking at resistance. This top one is off of the Vicor meter, again basically a Harbor Freight meter. The next one down is our ZT102. You can see that's at basically 0.0115 ohms versus 0.004 ohms for the Belden. And again, you can see what happens when we change to the next range. See, that Belden wire is fairly stable. You can see the resistance of the ZT102 just basically goes into thermal runaway, and eventually it just blows open. Well, I think that's going to be it for this video. Hopefully you found it educational, maybe entertaining. Again, looks like the ZT102 that we've modified did pretty good with the testing. I wasn't really sure what to expect with the current input, but looks like the fuses that Dave sent were plenty fast to save it. Again, the fuses that Dave had sent me are a pretty decent fuse. They are sand filled, they've been certified. There was one thing about those fuses. I had a data sheet that I had found online, and when I ran some tests on those, the fuses that I had received from Dave didn't match the data sheet. So I had asked Dave about it. He ran a bunch of tests, and it turns out Dave actually had a different data sheet than I had. And so he talked to the manufacturer, and they actually had a third data sheet for those fuses. So if you're planning on using those, you want to make sure that you get the right data sheet for those. Well, I think that's going to be it for now. Until the next test later on.